In this short video, we're going to cover some basics on how to identify when to use the combined gas law. That's going to allow us to determine some unknowns, or well, a singular unknown variable about a gas under ideal conditions. In our previous examples, we only ever covered gases or gases within vessels when there were two variables given to us, right? Or an instance where only one variable was changing. So you may be asking yourself, what happens if all three variables change between an initial phase and or an initial setting, initial set of conditions, and then a second set of conditions, right? In this case, this GIF over here is one of the examples we can use for this, right? So initially, this tanker is filled with very hot, very hot water in a gaseous phase, right? And it has an initial volume with an initial pressure, and then as that water vapor begins to cool, condense, and drop the pressure, so there's a decrease in pressure, you see a drastic change in the overall shape or volume of this tanker, right? So in this case, our pressure initially decreases, our volume ends up decreasing at the end, and our temperature additionally also initially decreases to induce that decrease in volume and pressure. So in order to determine when you should use the combined gas law is when all three variables that we've discussed up until this point are changing, right? Again, so that's pressure, volume, temperature. So you could or should have an initial set of pressure, volume, temperature, and then you may be given a second set of conditions where the pressure is changed, volume is changed, and then be asked to determine the temperature or any combination thereof, right? You could be given the second set of volume and temperature and asked to determine the pressure. The important thing here is that with adequate information, using the combined gas law will allow us to determine unknowns about one of these gas variables. So let's jump into a practice problem. Okay, so let's get our first problem set up here, right? So initially, we have a very sturdy balloon that has a volume of 3.82 liters and is filled with hot air at a temperature of 452 Kelvin, and the pressure exerted on and within this balloon is 194.3 kilopascals. Now, we're going to bring that balloon out into the cold Maine winter weather that everyone's used to experiencing by now, I hope, and it's going to rapidly undergo some changes. So outside, it is 258.1 Kelvin, and the atmospheric pressure today is 106.2 kilopascals, right? So we're going to set up our problem. Right, again, note our initial conditions, P1, 194.3 kilopascals, V1, T1, P2, T2 are known, and what we're going to try and solve for here is V2. So let's set up our equation. Right, we have P1, 194.3 kilopascals times 3.82 liters, and that's V1, divided by T1, 452 Kelvin, equals our V2, which is our unknown that we're trying to solve for, our P2, which is 106.2 kilopascals, and I'm going to add liters here for our units on our volume, all divided by 258.1 Kelvin. Right? So we're going to, much like our other gas laws, we're going to cross multiply here. So we're going to bring Kelvin up into the numerator. We're going to bring, we're going to bring T2 up into the numerator, P2 down into the denominator, and set up our new equation. So that's going to be 194.3 kilopascals times 3.82 liters, now times 258.1 Kelvin in the numerator. Our denominator is going to be 452 Kelvin times 106.2 kilopascals, and we're going to set this equal to V2, our unknown. So now our Kelvin units cancel, our kilopascal units cancel, and we're left with liters in the denominator. So if we multiply across and divide, we are left with roughly 3.99 liters, right? Which actually means the volume of our balloon has gone up, So even though our balloon has been brought from someplace warm to someplace cooler, if you look closely at the values for our initial and secondary conditions, you'll notice that we go from a pressure pushing inward on the balloon as well as pushing outward on the balloon, right? Pressure inside is equal to outside, to a pressure almost half of that, right? So even though the balloon is getting colder, the pressure being exerted on that balloon has decreased by almost in half, allowing that balloon to expand a tiny bit even though it's cooler outside. Okay, that's some basics on how to use the combined gas law, which combines the three common gas laws we've talked about before this: Amonton's law, Charles' law, and Boyle's law. If you have any questions, please feel free to email me. Otherwise, I will see you next class.